us, there's like 41 slides, and at the end there's an assignment slide. So we'll have to see if we get to the assignment slide or not. We'll kind of see. So we'll come back to phase diagrams on Friday. All right. So I was looking at this, apparently the wrong part, but a lot of this stuff is very familiar. And so I don't know, we might get through 41 slides, because honestly, I mean, you guys know this from Chem 1, that we use the term solution to talk about a homogeneous mixture. We tend to think that the solute is in minor amount and the solvent is in greater amount. Remember that? I hate the S's. Okay, so solute is dissolved in solvent. It's possible you could have 2 or more solutes that are dissolved. And it's also possible that your solute could be a solid or another liquid or a gas. And your solvent could be a gas or a solid or a liquid. And we talked about aqueous solutions, of course, have water as the solvent. And so we've been kind of talking about miscibility and immiscibility. We've been talking about preparing solutions. So 2 or more things that are just physically combined in a homogeneous mixture. Okay, so this actually, we're going to build up to how do you describe how concentrated the solution is. And we're going to talk about molarity again, moles of solute per liter of solution. We're going to talk about grams of solute per liter of solution. And in those cases, actually, those are the amount of solute per given amount of solution. We're going to introduce something in this part called molality. And I'm like, could you not have come up with something that was less like molarity? And as it turns out, molality is moles of solute instead than per, it's actually kilogram of solvent, not solution. So we kind of break away from that amount of solute per amount of solution in molality. So this is kind of, you guys got this, right? Concentrated means there's a lot of solute per given amount of solution or solvent, and diluted means that there's not much, okay? So it's just kind of generic terms. All right, so here's our list of 6, okay? Now these are 6 different ways to describe how concentrated the solution is. Some of these we've talked about, some of these we haven't. Some of these we've talked about. I'm just going to kind of remind you about them. I will say that these different ways of expressing solution concentration, the problems that you're going to have at the end of this part, whether we get to them today or we get to them Friday, the problems that you have basically say, here's my solution. How do you express its concentration all these different ways? So you're going to have to be able to kind of go back and forth between these different ways. Mass fraction and mass percent, that's weight percent. We've kind of done that before. Mole fraction, mole percent, that's the relative number of moles of solute to the total moles in the, so you'll probably be okay with that. We did mole fraction when we did, maybe we didn't. Volume fraction I don't do much with. Now these 2 that have the red bracket around, we definitely covered in Chem 1. Simply, and we're going to do an example coming up, grams of solute per liter of solution, moles of solute per liter of solution, okay? Of course, moles of solute per liter solution is molarity with a capital M. And then I mentioned actually molality. And actually molality is one of the ways of expressing a solution concentration that we really need to go further with this unit 1 in here. Molality is, I'll go ahead and put it up here. That is, it means moles, are you serious? Moles of solute per kilogram of solvent. That's what molality is in a nutshell. Okay. Now the cool thing about molality is notice that volume is not involved like it is in the grams per liter and moles per liter. And since volume isn't involved, you can be at any temperature. And molality would stay the same. The volume is kind of a your glassware has to be, at 20 degrees and that sort of thing. So volume's kind of a moving target. So I'm going to kind of talk you through a few of those. Mass fraction is kind of like weight percent, but it's kind of just short of it. So hopefully this kind of rings a bell. Mass fraction is grams of the component per 1 gram of the mixture. Yep. And that's what it means, but if you need to calculate it, basically, you go ahead and set aside the mixture, you isolate A, you get the mass of A divided by the mass of the mixture, and that's it. That's your mass fraction. Now, mass percent is related to mass fraction by multiplying it by 100. So mass percent, sometimes I'll put the thing percent after this. If, in some cases you will, you already have the mass fraction, if you multiply it by 100%, then you have the mass or weight percent. Mass percent, weight percent, it's the same thing. Of course, to unpack that, what that means is the mass of the component in 100 grams, or 100 parts of the mixture. There we go. So in other words, if you didn't have the mass fraction, you could just go ahead and take your mixture, okay, get the mass of your mixture, tease out your component, take the mass of the component divided by the total mass of the mixture. And to get it to a weight percent or mass percent, you take it times 100%. Okay, this feels Gen Chem 1-ish, right? So again, kind of Gen Chem 1-ish. In fact, I'm not sure if I didn't just steal these from Gen Chem 1. So let's just say someone has a sucrose solution, and they say the mass fraction. Mass fractions will always be less than 1. The mass fraction is 0.159. We need to be able to unpack. We did a lot of unpacking in Chem 1. This is kind of another way to unpack. So when it gives you the mass fraction, that means in 1 gram of the mixture, in this case solution, you have 0.159 grams of the component, in this case sucrose. Be able to unpack. And then for that same solution, if somebody says, all right, well tell me how concentrated it is in weight percent, you just multiply by 100. So instead of being 0.159, it's 15.9%. You okay with that? Okay. I thought so. See what I mean? 41 slides. You know. Okay. So, dilute solution, we said, is kind of the opposite of concentrated solution. But how dilute is it, right? I'm actually going to throw one more in addition to the list. Okay, I'm going to throw in environmental samples. A lot of times we'll talk about parts per million, ppm. Okay, and that is related actually to weight percent this way, or mass fraction, I guess I should say. If you have the mass fraction, and if you wanted to get it to parts per million, instead of multiplying by 100, you have to, guess what, multiply by 1,000,000, okay? So if you know the mass fraction, multiply by 1,000,000, you get the parts per million. Makes sense? So here's one for you. I mentioned that a lot of times parts per million is reserved for environmental samples, okay, because they're pretty darn dilute. If it is an aqueous solution, environmental solution, if the solvent is water, then actually we have this kind of neat thing, and again, it's not listed on your list of 6 ways of describing how concentrated a solution is, but parts per million actually approximately becomes milligrams of the solute per liter of the solution, if it's dilute, aqueous. And you can convince yourself it has to do with the density of water. What's the density of water in grams per mil? 1, yeah. So if you kind of chase that down, you can do a factor label problem and convince yourself. So this is kind of a nice one to kind of, that's the blue box. Okay, if it's an aqueous solution, parts per million is the same thing as milligrams of A per liter of solution. All right. Mole fraction. Mole fraction actually is another one that we're going to want to be dealing with here still in Unit 1. Mole fraction and molarity. Did we talk about mole fraction before? It's not too bad. Basically, again, you take some material and you're like, okay, so this is my mixture. You count the moles of everything and you put that in the denominator. And then you put the moles of your component in the numerator and you take that's it. That's the ratio. Mole fraction. That's totally it. Okay. Mole fraction, I guess we didn't talk about this. Mole fraction, the symbol for mole fraction is X. and you say the mole fraction of what, and you put that of what as a subscript. So this would be the mole fraction of component A. And like if you had, a mixture of 4 things, A, B, C, and D, does this make sense that their mole fractions would add up to be equal to 1? Okay. Yay, we're on the same page here. Okay. Yeah, I thought this was, I don't know, it's been a while, but, so we talked about, if you have, what's that? You don't have the slide? Oh, slide from chemistry 1. Dalton's law of partial pressures. Dalton, and I'm like, oh, Dalton, you're so smart. Dalton just said if you have a box where you have, we have gas A, gas B, and gas C all in there bouncing around, he basically said that the pressure of A plus the pressure of B plus the pressure of C is equal to, bless you, they're additive, the total pressure. And that's Dalton's law of partial pressures. And then, actually, we have kind of this cool thing going on. Did we? Because we did the, okay, watch this. PV is equal, I tried to find this. If you guys recognize the ideal gas law equation, okay? So basically, we can take the total number of moles, total pressure. Did we do that? Am I dreaming this? Okay, okay. They share a volume, okay, and they have the total pressure of in this case, 3 things, okay? Total number of moles, of course, are, and they're at a common temperature. So then we have this kind of cool thing that actually, for each of these partial pressures, we could say, for instance, the partial pressure of A is going to be equal to its mole fraction times the total pressure. Partial pressure B is equal to its mole fraction times the total pressure, etc. Yeah, mole fraction, gotta love it. And so for this one, all we would do is you'd have these gases, you'd know the moles of A, the moles of B, the moles of C, and that actually would go down here. And to get the mole fraction of A, you would go like this, right? That's it. Yeah. Cool. All right, so mole percent is mole fraction times 100%. We can do that. I mean, I've never done mole percent. I've done mole fraction, but never mole percent. But never say never. Okay. Okie dokie. And now again, back to kind of Gen Chem 1. Grams of solute per liter of solution. I actually have a problem coming up here. We can do that. For instance, if you were faced with this one, where basically the solute is sucrose, you're dissolving it in water. Doesn't it say? Yeah, water. You're dissolving sucrose in water. It gives you the mass of the component, 32.3 grams, and it gives you the final volume of the solution. So to get the, I'm gonna see it on the slides here, but to get it in terms of grams of sucrose per liter of solution, we're just gonna take those 2 numbers and divide it out. Now we have to fix it a little bit because we want units in the denominator to be liters instead of milliliters. So notice that, let's see, oh, wait a minute. Wow, what is that? Is that really, or I guess we're just missing the term, 1,000 over 1 liter. Where did it go in my slides there? It's funny, this says it cannot show it. Really?
It's there.
What's that?
We can imagine it's there.
Yeah.
We're all familiar with names.
Yeah, thank you. Oh, that's so supportive. We'll just kind of write it in there. Do you guys already have these? Oh. Okay. Yeah, so go ahead. Go ahead and write 1,000 milliliters. It did. It's got like a little graphic there. I've seen this in PowerPoint before. over 1 liter. So basically you multiply these two terms, okay, rounded to, we're going to have to round correctly. Notice that we're rounding according to 3 sig figs, which is great. So our calculator displayed 3 sig figs 144, and units would be, usually I'll just write it like this, grams per liter. And that's the formula for sucrose. Okay, that's weird. All right. What's that? No. Yeah, no, I'm just sitting down because I can. Yeah. So molarity is kind of like the whole Chem 1 thing too, right? So anytime somebody gives you the molarity, that's moles of the component per 1 liter of the solution. So again, you're going to need to unpack, I call it unpacking M. So what does M mean? Moles per 1 liter of solution. And I have, so for instance, if somebody says that, you know, it's 3.0 molar, of course they're telling you there's 2 sig figs, so make sure you don't lose that trailing zero after the decimal. That means 3.0 moles of HCl per 1 liter solution. And remember that this 1 down here is exact, but like I said, you have 2 sig figs there. So I tell students I should never see a big M when they go to do a calculation, unless it's M1V1 is equal to M2V2. That's fine. Okay, so this is a molarity problem. Again with the sucrose. So you basically we're taking a certain mass and dissolving it. I think it's the same. The 144 grams per liter, we're going to basically piggyback off of that. So in order to come up with molarity in this sort of problem, we'll need the molar mass of the compound. So we take 12 times 12.01 for carbon, plus 22 times 1.008 for hydrogen, plus 11 times 16.004 for oxygen. And rounded to 2 decimals, we're looking at a molar mass of 342.30 grams per mole. So again, that's grams per mole. Make sure we're going to factor label that thing. So if we piggyback on the sucrose solution we were looking at before, where we came up with 144 grams of sucrose per 1 liter of solution, okay, so what could we insert there then to make units of grams cancel and be left with moles in the numerator?
342.3 grams of sucrose per 1 mole.
Yes, and then how does that, but if we put grams in 1 mole, grams aren't going to cancel, so.
Yeah, put grams at the bottom of the mole.
Yeah, grams on the bottom mole. Yeah, you're good. Yeah, I know that's what you meant. But yep, grams on the bottom, moles on top. You got it. You got it. So units cancel, and we're left with units of molarity. Moles of sucrose per liter of solution, which is great. Looks like we still need to round it to 3 sig figs, and I got 0.419. And usually I would write it 0.419 m. Now, you know, you pack it back up again. 0.419 m molar sucrose. It's all about getting the units that you want.
And on our homework, we can write it either way.
Yes, the answer, definitely. On your homework, you can just write it either way. Yep. All right. So now on to molality. And I already told you molality is moles of solute, I said, per 1 kilogram of solvent. There you go. Molality, the symbol, and you're like, they could come up with a different symbol. What's the symbol for molarity?
Capital M.
Capital M. The symbol for molality is a lowercase m. Are you serious? I mean, just setting us up for failure. okay? So molality is definitely different than molarity. I guess the only biggest difference is the denominator. Instead of liter of solution, it's kilograms per solvent. Kilogram of solvent, 1 kilogram of solvent. Yep. So, if the amount of component you have dissolved in water is very dilute, and you can convince yourself why this is, then I guess the volume of the solute isn't significant, and the density of water is 1.00 grams per milliliter. Those two things come together, and your molarity is approximately equal to your molality for dilute aqueous solutions. Yeah. So, but you guys, that whole approximate, you know you're not going to be able to use that in Gen Chem, so. But it's something to keep in mind. We kind of talked about this earlier, since molality doesn't have a volume component, and volume changes with temperature, okay, then your molality is steady, independent of whatever the temperature is. So it's just simply moles of solute per kilogram weight of solvent, unlike molarity. Molarity does depend upon temperature, because your volume's kind of. That's kind of nice. So the thing to look at here, these are 2 potassium dichromate solutions, and you know how, I think we've talked about, these are volumetric flasks, and they have one gradation on them to basically tell you, in this case, that at that gradation it holds 1.00 milliliters. What, you know what I mean? 1,000.00 milliliters at that mark. So what somebody did over here was to take, basically take 1 mole of K2Cr204, oops, potassium chromate, not dichromate. Oh, anyway, so they took 1 mole of that, and they put it down here, and then they added water to make 1 liter. So that was 1 mole per liter. And this one, what they did was they added 1 mole of the solute, and then they also added 1 kilogram of water. So not so surprising, the volume of the solute basically made it so it's more. And just looking at this, does this make sense then? If you get dilute, okay, I guess you should be here. If you have less and less and less of your solute, can you see where molality approaches molarity for dilute aqueous solutions? All right. Actually, I told you wrong, because they're 0.1, they're not 1. So in both cases, it wasn't a full mole, it was 1/10 of a mole. All right. All right. Dang, that went fast. Because I think we just do this problem and then I turn you loose on your own problems. Okay. So for this one, what I encourage you to do is to, you don't have to draw a picture, but you do have to unpack. So I'm going to draw a picture, and it's going to represent nitric acid. And then I'm going to unpack that 70%, I'm going to unpack the density. Okay, it's like a brain teaser. Okay, so here's my nitric acid. You know, T is equal to 20 degrees, which we don't really care this time. But the weight percent, okay, that's 70.0% HNO3 means that there are 70.0 grams of HNO3 in 100 grams of the solution, right? And the density, the 1.42 grams per mil, means that there's 1.42 grams of solute. This is for the whole solution. 1.42 grams of solution per 1 milliliter of solution. And then the questions over here are to knock out molarity, molality, and mole fraction. So a lot of times, I will kind of go ahead and say, what is molarity? So question mark molarity, and that is moles of HNO3 per 1 liter solution, okay? Question mark molality, little m, and that's moles of HNO3 per 1 kilogram of H2O. And then last but not least, mole fraction of HNO3. That would be moles, and I'll use N for moles, moles of HNO3 divided by moles of HNO3 plus moles of H2O. To me, this is kind of important, this kind of looking at it right off the bat. So I can't remember how much of this we did in Chem 1. But we're going to have to, in a minute, come up with a basis and basically a starting point. That our basis is our starting point and kind of work the problem from there. I've kind of done a couple background calculations here. This is the molar mass of nitric acid and the molar mass of water. You guys have these. This is just kind of background information. We'll see how this kind of falls into place. So your basis could be 1 liter of solution, but as you see here, here's why would you go 1 liter? Well, I don't know. But to me, what screams even more is the one I'm going to go with. We're going to go with 100 grams of solution. Okay, so a lot of times if I'm working this, I will say, assume, because you can do this, assume you have 100, we'll pick it in, we'll kick in another decimal, 4 sig figs. Assume you have 100.0 grams of solution. That's your assumption, and that's fine as long as everything's kind of relative. Things start to kind of fall in place. The reason I picked that is if I have 100 grams of solution, I have 70 grams of nitric acid. How much water do I have? 30, yeah. So things start to kind of fall into place. Right away, can you see where I could actually knock out, just based upon that, I could knock out mole fraction. Because I could use the molar mass and the mass of nitric and the mass of water you told me to get to mole fraction, exactly. Okay. So I'm going to kind of show you, oh, it's already up here. You're going to show you kind of how this goes then. And there's different ways to work this. Definitely different ways. You don't have to go in this order. You could choose 1 liter and it still would work well. So if I have this mass of solution, can you see where I can use density to get to volume of solution? Yeah. And that's what this is going to show you. Okay, you start as your basis, 100.0 grams of solution. We want grams to cancel, so what does the next term look like? Yep. So we want grams to cancel, so that looks like,
It'd be 1 milliliter solution.
yep, 1 milliliter solution, yep, over that 1.42 grams of solution. Now how do we get it to liters?
1,000, actually it'd be 1 liter over 1,000 milliliters.
Yep, 1 liter of 1,000 milliliters, exactly. Oh, I guess I didn't do that. I'm kind of surprised I didn't do that. There must be some reason, but you're right. Okay. So how are we going to get to moles of HNO3?
So do we want to keep it in milliliters, or do we want to take it?
I think I was kind of surprised at my answer
Yeah,
key. I would take it to liters.
Yeah, that
But-
stayed to move.
Yeah, I would take it to liters. But the next one, how do we get to moles of HNO3? Yeah, you use your 70.0 grams. So we take our 70.0 grams as our first term. Our next term is the molar mass you saw in a few slides ago. We want grams to cancel. So the molar mass looks like this. It's what I call the flipped version of the molar mass. 1 mole of HNO3 over 63.02 grams of HNO3. That's molar mass. Allowing 3 sig figs. The moles, or the N of HNO3 is 1.11 moles. That's cool. We'll do a similar thing. You guys told me 30 grams for water. So we go with that 30.0 grams over 1. Use the flipped version of the molar mass of water, which I bet you guys know the whole 18.02, right, by now? So 1 mole of H2O over 18.02 grams. Grams cancel, we're left with moles of H2O. I got 3 sig figs, we're looking at 1.66 moles of H2O. So can you see now where, actually, we're about ready, we can do this one up here too, can't we? The whole molarity. All we gotta do is moles of HNO3 we got there, divided by that volume, which I wish it was liters, to go ahead and get molarity. We said how we can get this one. Do you see where, actually, we can actually knock out this middle one? Because we got the moles of HNO3, and instead of, what was the mass of H2O?
It was 30.
Oh, you're right, 30. Thank you. Is that 30? Yeah. So we're almost done. I mean, I hate to say we're almost done, but we're almost done. So here we go, knocking out molarity. I'm like you guys. I think I would have taken this all the way to liters, and I'm going to have to fix this. But here's tacking on that term that you might have tacked on earlier.
Yeah.
If we take the moles of 1.11 moles of HNO3 over the volume of 70.4 milliliters, and then insert 1,000 milliliters over 1 liter, round to 3 sig figs, you're looking at a molarity of 15.8. Seems pretty high. 15.8 molar. And again, it's kind of like Olivia said, I would just probably put a big M there instead of moles of HNO3 for 1 liter of solution. Same thing.
And then on our exam, would you rather have that or just a big M?
Big M is what I'm used to, yeah.
Okay.
But if you use it in a problem, you have to unpack it.
Yep.
Yep. So there's that one. Ta-da! Okay, so the molality is moles of HNO3 per kilogram of water. You told me 30 grams of water is what I had on my basis. So I'm back to that 1.11 moles of HNO3. The mass of water was that 30.0 grams. Now, this is not molality. It needs to be per kilogram of water instead of gram. So we can fix that by doing what?
1,000 grams over.
Yes, I always have to concentrate. It is, yeah, 1,000 grams over 1 kilogram. You got it. And that would give us the right units for molality. 3 sig figs, I got this. That seems like a big number again. 37.0 molal. And again, I would just put the lowercase m. Molal. So we call it, molality is molal, molarity is molar.
Wow.
Molal.
So moles per kilogram, preferred lowercase m for that, is what we're saying?
Lowercase m, yes. Yep, lowercase m. That would be great. So mole fraction. Okay, we can do this. So in the top, we're going to put the moles of HNO3. In the bottom, we're going to put the moles of HNO3 plus the moles of water that we came up with. Mole fraction, kind of like mass fraction. Basically, we allow those moles to cancel, those units to cancel, and mole fraction is going to be unitless. So remember, this should always be less than 1. So rounded to 3 sig figs, I get 0.401 mole fraction. And actually, this could be, I'll go ahead and, we've been talking about how you could, how do I want to say this? Instead of doing this, you could simply put 0.401. That's the, with no units. That is the mole fraction of HNO3. Any questions about that? So let's see, if I were going to go, instead of my basis is like that, I focused on this. If instead we focus on this bit of information that was given and basically kind of scale up from here, if we go, for instance, with a liter of solution, then move the decimal place over like 3 places, that means we have 1,420 grams of solution and kind of go from there. Then we could use the weights percent to see of that mass, how much was nitric acid, how much was water. So we could kind of backtrack it that way. But I do think it's good to kind of think of it as kind of getting pieces, and if you have an assortment of things you're going for, then kind of assembling those pieces, I think. That's what I've seen. Okay.
So for the mole fraction, we're gonna go with the total moles of the entire solution.
With the mole fraction, the total moles of the entire solution at the bottom, yep.
Okay, that would have screwed me up, that's what I wanted
Yep. All the moles, and if you have more, this was just 2, this was nitric and water, but if there was a third component, it goes down there, and then the component of interest goes at the top. Yep. I guess I show you how to do it this way. Well, let's see. Okay, 1 liter of solution. Then we can use this to get to the mass of the solution. So we have to convert that to milliliters, somewhere in there. I would have kind of put the last term, second term, but that's okay. Where that third term is density. So this is going as the different bases. So assume you have 1.00 liters of solution. This is an alternate way to work it. We should get the same thing. But I like this, going ahead and saying what your assumption is. So around to 3 sig figs, we have the mass, like I said, is 1,420 grams. So the mass of nitric, then, we're going to use the weight percent. So we're going to use, this is our starting point, 1,420 grams of solution. And then we use this to our advantage. We want grams of solution to cancel, so we're going to use the unflipped version. Okay, 70 grams of nitric over 100 grams of solution. Rounded to 3 significant figures, then your mass of nitric. Now everything's a little bit more, isn't it? Your mass of nitric is 994 grams of nitric, pure nitric. You can get the mass of the water 2 ways. You can get it by difference, or you can go ahead and get it by percent. I can't remember what I did here. Looks like I got it by percent. So if it's 70% nitric, it's 30% water. So if we go ahead and take our the mass of our solution based upon our starting volume, and go ahead and recognize that we have 30.0 grams of water for 100 grams of solution. Around the 3 sig figs, that means that on that basis we have 426 grams of water. So we got kind of some different numbers there, but it should all shake out. So now we need to get some moles, don't we? So we're going to bring in the molar masses. Okay, I'll just put all these up here. So all we're doing is taking those masses we came up with the case of nitric, it's 994 grams of nitric times 1 mole over 63.02 grams. Now if I label it moles of HNO3, I don't actually include the species in the molar mass. So that leaves us with 15.8 moles of HNO3 in this scenario. For moles of H2O, we take that 426 grams of H2O times the flipped version of the molar mass of H2O, 1 mole of H2O over 18.02 grams of H2O, and get a whopping 23.6 moles of H2O. Now I think we're close to going ahead and knocking out all of our things over there. Those are kind of our pieces. You wouldn't have to do it in this order. Molarity is moles per liter solution. Well, that shouldn't be too bad. We're just going to take the moles we came up with, 15.8 moles, divided by 1.00 liters of solution. That was our basis. Round to 3 sig figs, we have our molarity then is 15.8 big M. Let's see, molality. Again, we're going to go with 15.8 moles of HNO3 over 426 grams of H2O. It should be moles of component per kilogram of solvent, so we have to fix our denominator, and we can do that by introducing 1,000 grams over 1 kilogram, rounding to 3 significant figures. We got a molality of 37.1. Is that what we had before?
37.0 for molality.
Okay, so it is a little different. So a little m there. Last one is mole fraction. So we're going to take the moles of nitric, 15.8 moles of nitric, divided by the total moles. That's 15.8 plus the moles of water was 23.6. It's funny how the nitric was more mass in weight percent, but it's in less mole percent, isn't it? Isn't that kind of cool? Okay. So round to 3 sig figs, and again, this can be unitless. You would just simply say, yeah, this one was the same, wasn't it? You would just say the mole fraction of HNO3 is 0.401. And that's it. I forgot I worked it both ways. I still think the first way seems more intuitive.
Say, which molality is more accurate? The one that's 37.1, one that's 37.1?
I don't know. I'd have to go chase it down.
I think it kind of depends on what information you're given for the problem, right? Like, the liter, the mass.
The weight we went with 4 sig figs, and volume we went with 3. You know what I'm saying? Because we went with 1.00 liters versus, I don't know. I don't see how that would make a difference. That one hurts my brain. It's rounding. It's all about rounding. So these will be due on Friday. Kind of take a look at those right quick. $13.11. I know, there's a lot of them. Okay, so you can see my unpacking up there for 11 in purple. How many liters should be evaporated to obtain 725 kilograms of pure solute component? So let's see, what are my notes up there? Oh yeah, the density wasn't given, they just gave you the, so, I don't know. Those are my hints.
I don't know.
I don't know. It's a puzzle, and I have to mull these things over, and I didn't recently mull them over. You've got time, you mull them over. But a year ago when I prepared this, I mulled it over to the point of, I'm like, oh yeah, that's how you get there. So the next one, you're trying to, they give you the volume and the target molarity of the solution you're trying to make up. And it says, how many grams would you need if you know your sample is impure, is only 99.81% silver nitrate by mass. So I kind of have the hints down there. So some of these you kind of backtrack. So in this case, my hint was to take your target volume and your target molarity to kind of backtrack to the amount of the AgNO3 that you needed. Okay. So that's my hint there. Whoops, sorry.
Would you recommend taking the 125 milliliters, turning it to liters, and then going into moles per liter? Right?
I think that's part of the backtracking.
Yeah.
Yeah. I would use that volume. My first step would be to convert it to liters so I can use molarity to get to moles. Yeah. And then to grams of pure substance, and then the weight percent to get to the impure you'd need. Yep, I agree. And then this one, they give you the molarity of the sulfuric acid, give the density, and they're trying to find the mass percent. So this one's kind of similar to what we were doing. You weren't given weight percent, but you were given molarity. So I would take as my basis maybe 1 liter of solution and kind of go from there. Is that what I said? Yep. That's, I mean, you don't have to, but that's what I would do. And so for this one, oh, we haven't talked about the square brackets. We'll be talking more about those, but it gets kind of cumbersome writing the M, okay? But anytime you see square brackets, they mean molarity, okay? So, yeah. Of course, SO42 minus is sulfate. So, and this is where you need to go back to parts per million in this dilute solution. Is that part of my hints? Oh, come on. For dilute aqueous solution, ppm is approximately equal to milligrams per liter, and you're going to use that. So count on that. So if your target, or, okay, and the information given, so I would get the molar mass of sulfate. Oh, say, yeah, you're not too bad. If this is the case, all you gotta do is convert milligrams to grams and then use the molar mass. And then you're there, right? You know, that one's not too bad. Not that the other ones are, but. Okay. So in this case, they give you the weight percent, phosphoric acid gives you the density, and you're asked to find molarity. Now this one is just like what we did, except you're not finding a whole bunch of things, just molarity. And I kind of like the weight percent, but you could do the volume too. This one, you're after molality, which is moles of para-dichlorobenzene per kilogram by dissolving. So, oh, see, this confuses me. So you're gonna, the DCB stands for dichlorobenzene. So that's the mass, and you're gonna dissolve it, not in water, because it's wouldn't dissolve, I guess, but you're gonna dissolve it in benzene. Okay. So you're after, little m means molality. So basically you're, the D, again, the DCB, and actually up there in purple I say what it means, that you're after the moles of that in 1 kilogram of benzene, basically. Okay. And they said that actually the density of benzene is given right here.
Yep.
So, oh, it's dissolved not in a total volume, but the volume of benzene is 50. So you can use, it's not too bad, you can use benzene's density to get to the grams of benzene.
Yeah.
Yeah. And then you're just after basically taking that mass of dichlorobenzene, using the molar mass to get to moles. You take those moles and then divide it by the mass of the benzene. It's not too bad. None of these are too bad. Me and my beakers. Okay, aqueous solution, not dilute, right? Again, phosphoric acid, it gives you the weight. Do we do this one? Molarity. Seems like, did I go backwards? This one's very similar to these. Okay, I guess I didn't go backwards. In this case, you're supposed to calculate the mole fraction of each one of those. So, let's see what my hints are. So the first one, it gives you weight percent of ethanol. And again, feel free to make your own abbreviations. I would go, again, as the basis is 100 grams of solution. In that case, then, that means that it's an aqueous solution. You have 21.7 grams of ethanol. And for this, and then not go to, you have to get moles of water, you'll get grams of water, and then it's very similar to this. For this one, you're given molality, you're trying to go to mole fraction. I would suggest using, as my basis, 1 kilogram. Do I say anything else? Nope. So if you go 1 kilogram of water, yeah, 1 kilogram of water, can you take this moles and come out with the mass of urea? I guess you don't need to know that. Calculate the mole fraction. Oh, that's not too bad. So you can use the molar mass of water. I'm sorry, I'm drawing a blank. You can use the molar mass of water to take 1 kilogram, see how many moles of water in 1 kilogram. And then you take those moles plus these moles, and that's in your denominator. All right, I got it. Okay, the last one. Calculate the mole fraction of these, it's kind of similar to what we've been working. I would go with 1 liter as the basis for the first one. I would go with 100 milliliters as the basis for the second one. That's
It's
it.
a big old batch of homework.
It is a big old batch.